Oh, wait.
You don't like that?
We're live. All right. Hey guys, welcome back. It's week 10. What is better? What is better? Okay. Welcome back to RC3. Anyone new this week? No? Yes? All right. Okay. Sure. Yeah.
Nobody takes it seriously week 10. Cool.
But-
Wait, over there. No, are you actually new?
Are you? Okay. Well,
Welcome.
welcome. What's your name? Nice to meet you.
Hi, Ryan.
It's with a B. Brian with a B.
Oh, I fucked up. Sorry.
Cool. So yeah, otherwise RC3, sign-in.rc3. You guys will find that the sign-in form has changed. We're adding in some polling questions just to kind of like improve ourselves and stuff. Cool. Awesome. Yeah. Otherwise, so welcome back, everyone. Otherwise, usual mashup of links there. Slack, newsletter, site discussion, demo help. Oh, that's not there. Oh, no, that is there. Okay. Otherwise, demo help. Otherwise, the important dates and times have changed. So remember that the RC3 CTF is November 17th to 19th. That's in like a week or two. 2 weeks. Yeah, 2 weeks. You can sign up there, so rc3ctf.rc3.club. Otherwise, if you missed the ShmooCon ticket sale yesterday, 2 days ago. Wow, okay, 2 days ago. It comes out December 1st again, so we'll get back here. We'll try to order more tickets. Otherwise, the Penn State Hackathon is this weekend. Some of us will be going, just the talk there. Yeah, that's it. So if people know about RC3, that's why. The Grim October CTF, like their monthly thing, is over for this month. You can see the write-up on that link, that Google link over there. But Jamie's working on the November one. It'll be out soon.
Monday.
And otherwise,
It's out Monday.
Monday. All right, it'll be out Monday. So be excited, get hyped. Otherwise, the CPTC competition is this weekend. So good luck to our team and good luck to all the other teams that will be here
Labs.
eventually.
The labs. Say that.
Oh, so the labs will be closed. So if you guys have homework and stuff, don't
You can.
do them
Just
on the weekend.
Saturday.
Yeah.
Saturday.
Just Saturday. Yeah, so just cram it all Sunday. Otherwise, Woodard, if you guys don't know, we record Answer in the Woodard Studios, so huge shout out to them. But they're also hiring, so if you're interested in being a web developer or a staff engineer for them, it's about 4 hours a week. It pays. The pay varies. You get a lot of experience. They're really cool people. They do a lot. So yeah, but otherwise, how's everyone doing? We're wanting to do a quick CTF check-in since the CTF is in 2 weeks. Does anyone have any feedback for us? What they don't like, what they like? Did you raise your hand? Or? Oh, okay. Otherwise, any questions? Do you guys feel prepared for the CTF?
Yeah, well.
What's up?
We do not feel prepared. What can we do to feel more prepared?
So there's the CTF field guide. If you look that up, it's like a giant collection of resources for you to use. That's a really good primer to CTFs. Otherwise, I mean, the challenges are kind of similar to what we do every single week, except harder and more convoluted and stuff. But yeah.
Also, go check out old CTFs. Find write-ups. There's tons of them. There's a GitHub that has a shitload of them that you can look at, or just find various people put like blog posts. For example, like Joel has a couple blog posts on various CTFs he's done.
Ben has a blog.
Ben has some, maybe. He has a lot of like sysadmin stuff.
Yeah.
Anyway, like just look up old CTFs, because while security is very big, there's only so many different things you can do for challenges. So there'll probably be at least some challenges that are similar to other ones.
Yeah. Does everyone who wants to participate have a team, or do they need to be paired up? Are you by if you're by yourself, raise your hand. All right, you guys can talk later. Right?
We should make a form.
Yeah, we should make a form. All right, we'll drop a form. Yeah. Any other things? Maybe. Yes. No. Anyone feel ready? Anyone? Okay. Otherwise. Okay, that's fine. That's okay. We'll see. Otherwise, so since we know that a bunch of you are going to be away at UB that weekend, we're going to be... Oh. All right, got it. Cool. We're going to be extending... So we're not going to score it. So Sunday night, that's when scoring stops, but we're going to extend the entire competition. We're going to keep it up for a week until Friday, so for you guys to play around and then, like, like still work on it and stuff, and then we'll be going over it the following Friday. So no worries if you ended up missing out on it. I know we'll miss some of you, but also November 18th we'll be here in the Sec Lab. We'll have like food and all that and stuff. So come hang out, do the CTF with each other. You know, if you help each other, you guys all win, and it's good. Don't do that. Otherwise, so huge thank you to our sponsors. We actually just had HackerOne and Trello sign on. HackerOne sign on is gold. That's the bug bounty thing. They're really cool. I think Yobert is like the guy who does it. He's really dope. Otherwise, we have Trello. We now are super agile. Yeah. So otherwise, everything we teach is for educational purposes. And, you know, don't do bad things or bad things will happen to you. You've been warned. And without further ado,
Simon.
Yeah. All right, so
it's my joke.
today we're going to be talking about some reversing, because that's how I feel whenever I tried learning all of it this week. Yeah. Okay. All right, so basically what reversing is it's just looking at something or some process in a different way and trying to like backtrack through it and how it was started. So I'm sure most of us in like first grade, you guys remember how somebody in your class would take a little spring pen and like take it apart and flip the spring around, and all of a sudden you'd click it and the pen would shoot out. That could be it could be almost like considered reversing, because you're looking at how the pen works, right? You're figuring out the mechanism behind it. You're changing it to do something different in what you need it to do. So in CSEC, whenever we say reversing, we think of the terrible writing that is assembly and the headache that it causes everybody whenever they look at it, except for Brad. He loves this stuff. But there's a lot of different types of reversing, so if assembly is not your thing, don't worry about it. So reversing's Who Am I page, there's some static analysis, which is basically you have a whole bunch of assembly and you're just straight up looking at it, okay? You're not really doing any fancy tricks with it. You open up like IDA or some other disassembler and you're staring at it and trying to figure out what the heck's going on. And also that's where the headaches come in. If you're lucky enough, you get some pseudocode to look at, but most things you won't get that, so you'll just have to be dealing with the raw assembly. Then there's dynamic analysis, which is where you attach like a debugger to the program and you're actually following what it does as it's executing instead of looking at just the assembly output. And then how and why, as I said before, you're just looking at a program. You can maybe write hot fixes for things if you're having a specific bug. Just figuring out how things work for educational purposes or for a different reason. Obviously we don't support any of that. If what you choose to do is your choice, but knock yourself out. So why do reversing? Malware analysis. If you have a nice piece of malware that's messing with your system, you can try to figure out what's going on with it, or same with it at a company or something. Exploring closed source software, so figuring out how it works, maybe writing a cool little fix for it, adding in your own feature that you want a program to have. Or if you're a masochist, you can also do that, specifically at Brad. Again, improving software, and then we have a little disclaimer, just don't be dumb, as I said before. Alright, let's get a little bit technical here. So you're going to start with a binary file, okay? And that comes from compiling usually just a C program, okay? That's what an executable is. So what happens is it goes through, takes all your code that you wrote, and then it converts it into the machine language, and then your processor executes it, okay? So then what you see is then the assembly output, which is the readable version of that binary that we just compiled, okay? And then there are different syntaxes. There's Intel syntax and AT&T syntax for your for the assembly. All the instructions are the same, but they're just going to look a little different. Also, there's the machine code becomes those registers right there, and also shoot, what are the moves called? Instructions. Yeah, my bad. So then the machine code is just the binary. There's a lot of different terms that are like almost interchangeable here. More terms. A disassembler, it translates that binary into the assembly. So whenever you run it, it's just going to give you that headache on the terminal. And then the decompiler, it reverses the binary. So sometimes they'll give you some pseudo source code, and then so you'll see that with a lot of Android and Java apps. And then there's debuggers like GDB, where you can actually actively attach it to a program, and you can do things like set breakpoints in the program, so you can individually call functions and run those functions by themselves. Instead of like running the entire program at once, you can really test and dial in one specific part of the program at a time. So where does assembly come from? Basically compiling C programs. You got your languages there, which are your higher level languages, which then go down to assembly, which go down to machine language, which then go down to your hardware. And then so that's kind of like the hierarchy of how things go. So thankfully we only have to deal with the higher level stuff for the most part. Unless you like this, then go crazy. And then, so now Ohan's going to go a little more in depth into everything and try and explain the deeper things of assembly.
Cool. All right, thank you, Simon. All right, so assembly and reversing are complicated processes. Like, I can't tell you everything you need to know. I feel like I say this every week, but we're gonna do our best. So assembly is a low-level language technically, and as Simon was saying, it's assembly and machine language. So like the literal binary ones and zeros, that's where the word binary comes from when you think of a file, is actually a one-to-one translation. So assembly is just how we can see the actual instructions that we want the processor to run. So there's several architectures that you can program for. The most common ones are probably x86 and x86-64, which is the 64-bit version. And then there's some other ones like ARM and MIPS. ARM is like mobile stuff. MIPS is like, I think it's embedded. You'll learn MIPS in the concepts of computing that you take around your third year. You'll go into assembly in that, and you'll be writing assembly pretty much exclusively. You don't write. So for any of you that have taken mechanics, that's C, which gets compiled down into x86. But then when you take the next class in the sequence, you'll be just straight up writing MIPS. Which is kind of interesting. So how does this work? So you have instructions, right? That's how you tell what the processor to do. And you can kind of think about them like functions if you need to. Basically, everything that happens needs to be an instruction that the CPU will understand. So there's a handful of them. These are the x86 instructions. So I'm going to think this is, yeah. So you can move. That's basically moving something. Fairly straightforward. These instructions have to be very, very simple because it needs to be implemented in the actual hardware. There needs to be circuits that can understand what you're trying to do. Oh no. And have that happen. So kind of the three major things are instructions, registers, and memory. Hold on. Yeah. Okay. So registers are little bits of memory you can think of on the processor themselves, and you can store. They're used for like short-term storage, like local variables within like a function, say. And then memory itself. This is memory. This is your RAM on your computer, and this is where you can store stuff more long-term for the duration of a program. And you can store bigger things there. So if you have an array, for example, you would store that in memory, and then if you need to access an individual element, you would probably load that into a register. Do whatever you need to do, add, subtract, what have you, and then put it back in memory. So a little bit more about registers. I guess I kind of already covered this. So there's some general purpose registers in x86, RAX, all that. I'm not going to read them. And then there's also there's a couple kind of special registers. One of the more important ones being the instruction pointer. And so how that works is when you're executing your program, it's basically just a list of instructions, right? And you need to know, the processor needs to know which instruction it's going to execute next. So the instruction pointer takes care of that. It says, it's literally just pointing at, you have a list, and it's just pointing, it's like, okay, we're going to execute this one, and then we're going to execute this one. And we'll get back to this because this is important when you have conditionals. Writing code without conditionals is pretty boring, honestly. If you don't have loops or ifs, the program's pretty straightforward and not as powerful. So we'll get back to that. So a little bit more about registers. So in x86, registers are a certain number of bits long. And sometimes you don't need all those bits. So you can use a naming convention to access only a certain subset of those bits. So high to low order, it's fairly straightforward. So if you only need something that's 8 bits long, you can just use like an AL. Whereas if you have like a long, you would need the whole thing. So memory. Memory is very important. It's also very, very hard, no matter what well, not no matter what. If you're writing C, some of you probably run into like a seg fault or something. Memory is difficult. Memory is also, memory is difficult, and it's also very important because if you mess up, there's a lot of strong implications that can have. So we're not really going to talk about like exploiting that. We're going to do that next week. We're kind of coupling reversing this week, hopefully to give you a general idea of how like reversing works, how binaries like work, and how to look at them. And then next week, talk more about like, okay, now that you can like understand this a little bit, let's go ahead and like try to break it. So the heap and the stack. There's two memory constructs that every program uses, or at least has. So the stack, everyone's in CS1 or above, right? So the stack is just a standard stack, like the stack data structure. First in, last out, right? You push something on the stack, you pop it off the top, and that's how memory works. So you store stuff there, like I was saying. So you push on a variable. So you have, say you have a function, and there's a variable that you need in there. You can push that on the stack, and then to get it back off, you just pop it back off the stack. And something that can be kind of confusing is the way that it grows. So the stack starts in high memory, so the highest addressing, and it grows down to lower addressed memory. And the heap, which I'll get to in the next slide, starts at low memory and grows up. So they can meet in the middle sometimes. So the way that you actually access stuff that you put on the stack is through two more registers. They're the stack pointer and the base pointer. And basically, you access, so there's one at the, basically like the bottom and the top, and you can use an offset from either, yes?
Does that meeting in the middle cause a program to error out?
That's a good question. I think it doesn't happen, like, you have to really mess up for that to actually happen, but it can be a problem. So you can have an offset from either the stack pointer or the base pointer, and that will let you, and the area in between those two is called the stack frame. And this is really important, especially in recursive functions, is having a stack frame so you can isolate variables from function calls. So when you're writing assembly and you have a function, you need oh shit, sorry. All right, what's the best way to put this? You have, when a function gets, so assembly, right, is just a big list of instructions. And there's no way to like determine what, it's basically, you need to be able to differentiate. If you're calling a function, say multiple times, you only have a certain number of registers. So you can't just keep making, so like when you're writing like Java or something, you can just keep making new variables and it'll just work. And if you need to save something, you just make a new variable. But in assembly, you only have a handful of instructions, and so you need to manage everything by yourself. So if you make a function and it needs to store something or return something, but then it calls another function before it exits, you need to store that on the stack and then get it again when you come back. So the stack frame is very helpful. So when you're doing recursion, every function gets its own stack frame, and then that's defined by where the stack and the base pointer are.
And does ret pop off of the current stack frame?
So returning will destroy the current stack frame and put the instruction pointer to where, or like restore the instruction pointer to where it was before that function was called. So then there's the heap, and this is for dynamic memory. So if anyone's written C, Chris, you have a question? Sorry. Okay. So if anyone's written C, you have like malloc, for example, malloc and free, and that's how dynamic memory is allocated. So the heap you need to allocate yourself. So if you have some variable or something that you know is going to be, X bytes long, but you don't know what's going to be in it at compile time, you just want to allocate that space on the heap. And then once the program is running, it can write it knows that it has that much space to write whatever it needs there. And then when you're done, you want to free. We'll get more into this next week. This is like I was saying, memory is hard. You can mess this up all the time and break stuff. So this is a diagram like I was talking about of the memory segments of a typical program. The text section, this is where your actual instructions live in memory. So everything needs to get loaded into memory, right? Not just your variables and everything, but your computer needs to be able to know what instructions to run. So it has to load those as well. So those go down in the text segment, and then there's some unadditionalized data segments, and then the heap, which is growing. So it can there's no like standard for these pictures, which is kind of annoying. But so this is high addresses, and this is low addresses. So the stack is growing down, and the heap is growing up. So memory spaces. This is also important. When your program is running, it kind of just like has memory and it can use it. But what's actually happening is that memory is a shared resource, and you probably don't have a computer that's only ever running exactly one process at a time. If you're running an OS and then running your program, there's multiple things happening because your OS is running too. So the kernel needs to be able to protect that memory, because shared resources in computing is one of the biggest problems. If my program can change what's in your program's memory, I have control of your program, and I can do whatever I want, and that's bad. So there's something called memory spaces or virtual memory, and what that is it's the kernel saying like, okay, your program's going to need this much memory. I'm going to allocate that, but it doesn't all have to be contiguous. So the kernel will know, and it'll just be like, all right, so you can have like this chunk, but then like some other process already started, so we're just going to skip down to like right here and right here to your program are right next to each other. But in the actual physical system, they can be far apart. So programming constructs, like I said before, all code has to run on the CPU, so all code has to be written in assembly. So there's no loop instruction in assembly. There's kind of an if. There's kind of an if instruction.
Conditional jump.
Yes, but you need to be able to express that at a low level. So how does that work? They're called branches or jumps, and you basically have some sort of comparison, like a compare instruction, and then depending on the result of that comparison, say you want to see if EAX is larger than EAX or something. And if it is, you jump one place, and if it's not, you jump somewhere else. Or I guess more accurately, you don't jump and just go to the next instruction, because remember, everything's just a big list. So this is where the instruction pointer is really helpful. If you do want to jump, you change the instruction pointer normally when you're just executing, just goes to the next instruction, the next 4 bytes. But if your conditional is true, you can set it to jump. You can change the instruction pointer to jump somewhere completely different. So for example, if you're looping, you probably want to jump backwards. So normally you're just going down, right? But if you want to loop, you need to go back to code you've already run. So you move the instruction pointer backwards. So I think there's a picture on the next slide. Okay, so this is an if statement. This is the control flow graph from Binary Ninja, I think. And so this is like a C program on the side. Pretty straightforward. And then over here, this is the disassembly, and then Binary Ninja can do something called a control flow graph. It can recognize when there's if statements and kind of break them down for us so we can see
Oh, that's cool.
what would happen or what the possible paths through the program are. So for example, and then it'll even label them. So like if the check was false or if the check was true, then you want to jump and go here. So this is like a really, really simple example, but you can imagine this is really helpful when you have more complex programs. Something of note is I tried to like do this example myself, and I had it like if true, and the compiler actually optimized that out, and I didn't get this graph. So compilers are actually pretty smart and very helpful a lot of the time. You can write shit code, and
a lot of the times they'll just like make it better when they actually compile it, which is kind of nice from like an efficiency standpoint. So this is a for loop, a very similar type of simple example, but just kind of showing you like how things jump around, how control is or how the flow is executed. So we have like the beginning, like setting up the function, and then our for loop, right? I is less than 5, loop, print out I. So we can see if I is not greater than 5, yeah. So jump greater than or equal to is what this instruction means. So if it is, then we're done. But if not, then we do this, which is like the body of our loop. You can see like printf right here, which is right there. And then we're jumping back to the top of the loop. So there's a handful of tools. There's to some degree they're like kind of like they all do, or there's some tools that do similar things, and it's kind of just up to your preference. So we've listed a handful of them here. As Simon said, GDB, the new debugger. This can be really helpful. This is like a dynamic analysis tool. You can attach to a program and inspect registers as it's running, like call functions and stuff like that. This can, and also just help you debugging. It's not only used for reversing. It's a very good tool for all kinds of stuff. Object dump. This is just a disassembler. It will, disassemble the program for you, and you can specify which segments you want to read. And GDB can actually also disassemble for you, so it can provide both. Although neither of these have like the control flow like something like Binary Ninja or like Radar would have. Strings. This is like probably your most bare bones reversing tool that you can use. And what strings does is it looks throughout whatever you input to it, and if it finds 4 or more bytes that could be interpreted as ASCII, it just prints them for you. So if you've ever like catted a binary file, there'll be like some weird stuff. Your terminal might like break because it doesn't know how to handle those. It's trying to print bytes that like aren't printable, and it will just make everything look weird. So basically what this does is it just makes sure that it can be printed and then will print it. So if there, for example, is like a global string declared in a program, that will just be in the binary. So running strings will just show that string among other things, which can be really helpful. And then over on this side, we have some more dynamic analysis tools, such as ltrace, ptrace, and strace. These can be really helpful. So ltrace will show you when calls are made to shared libraries. So if you've written like C and you've done like include standard io.h, that's including the shared library, the IO library that allows you to do IO. So you need that if you want to do like printf. So if you if you use ltrace on a program, you'll see all the calls. For example, you'll see calls to printf being made. So you can see like what arguments are being sent to it, which can be helpful if you need to figure out if your program's doing something that it's kind of like offloading onto a shared library. This can help you figure that out. Ptrace is the underlying tool to like everything else, including GDB. And then strace shows syscalls. So this will show you like memory mapping. So like I was talking about the virtual memory stuff, that is actually a syscall, and you can see that with strace when you run a program. You can see that memory being allocated. Again, these can all like there's no one tool in reversing that is the sole truth. You need to do everything, and on top of that, you need to be able to. Brad unfortunately couldn't present today. I would have loved that. He's the reversing group leader. But I was asking him. I was like, all right, Brad, what's the most common misconception about reversing? And he was like, static and dynamic analysis are desperate. He was like, I always do both. You have a toolbox. It doesn't make sense to only use one tool. You want to use everything in there to get the job done. So static analysis, dynamic analysis, multiple tools,
I've seen Joel do reversing stuff. He uses IDA for 20 minutes, then he switches over to Hopper, then he switches back to Binary Ninja, then maybe he's got GDB open. Like, whatever tool is going to do the best for what particular thing you're trying to accomplish, you want to use that one. So you need to figure out what library is being called, use this. But then you're like, okay, like I know what that function does now. Now I need to go back into the assembly and see like where that call would go if I gave it this information. Maybe you want to pop open GDB and like figure out where that jump instruction is. All right, so there's some resources here. We kind of glossed over assembly itself. So I highly recommend this top video. This is by Hack UCF. They're a security club down in Florida. They're very highly competitive with us. They're usually like top 2 in CCDC. Where's Joel? Where's Joe? Anyway, they're very good. They were a very good program, and this is a very good video on like an introduction to assembly and how that all works. Much better than I could possibly do. Radar 2 is not on the tools slide, but this is a open source reversing tool. It provides some of the same features as like so the tools I was saying before, like IDA, Hopper, Binary Ninja. You pay for you pay for those. Radar 2 offers some of the same features, and it's open source, so it's free. You can always use it. And then there's a handful of other resources here. Simon made those. I'm sure they're all great. Are there any questions? I know this wasn't like the greatest presentation, but hopefully you at least have a basic understanding. Any questions? Anyone? These are all about like how I smell. So they think I smell. Yes. Yes. So they're on the RC3 website, rc3.club. You can sign in with your RIT Google account, and they should be right there, I think. Are they up yet?
They're not up yet.
They are not up yet. They will be up soon. Yes. Okay, so they're embedded. They're just a Google presentation. They're embedded, but they haven't been uploaded yet. So we'll work on that. Anyone else? Questions? Cool. So this is the Google Drive link. So I'll get the slides posted so you don't have to type that out. But I think the next thing is, so thank you. Did anyone get all the challenges from last week?
So
anybody? No?
No,
Okay. Does anyone want to know how to do the challenges from last week? One person? 2 people? Okay. We have. All right. We're gonna write it down. You want easy 3? What do you want, Ryan?
Ryan wants hard 2.
Hard 1 and 2. Okay.
We'll get those.
Any other challenges people want to see done?
Did everybody get medium?
Did everyone get all the mediums? Yeah. All the easies? All right. So Simon.
So we're trying this new thing where we're trying to get you guys talking more. If you solve the hard challenge over the week, just ping me or Ohad on Slack, and we'll try to get you up here and kind of like show off your hacker skills. Otherwise, this week, Kalyan solved the hard one, so he's going to talk about it and show you guys how to do it.
He can do that.
Yeah. Also, otherwise, that's the feedback link. We read it. We like legitimately take your comments into our e-board meeting, and we talk about it, and we try to do our best to make everyone have a good time. Otherwise,
hold on. It's gonna take me a second, but I think we can do it. No, they're literally all just memes.
you smell like blueberries.
Oh, okay. I smell like blueberries, not butterflies.
Yeah.
Whoever asked that.
Oh, dude, he can do hard 1, I'll do hard 2, then you do that one.
Yeah.
Okay, let me see if I can do it. Can you send me? Or
you can just do it online if you want.
You gotta flip it. I think you have to flip it around. Yeah.
Okay, so
Otherwise, introduce yourself. First name, or not first name. Sorry, name, major, and grade level.
I'm Kalyan. I'm in University Exploration. I'm a first year. So this week we had a bunch of encoded numbers, and a public key. And as you can see, the public key is very short, so you can actually brute force the solution. So this is an RSA key. So the way RSA works is this is a public key. So for making a key, you select two prime numbers that are supposed to be really, really, really big. But for this key, they aren't so big. And you multiply the two prime numbers, and the result is your public key. So if the result isn't that big, you can just brute force out the factors from that number. So we have this public key, and you can with...
Make that bigger. Can you make that bigger?
Wait.
Press it.
I don't actually know where to set the text size. Oh, here we go. If I do this and this and does that work? Okay, no, that doesn't work. Whatever, I'm gonna paste it into text editor so you can see.
Wait, say that one more time?
What? Oh, yeah. Okay, that's too big. Oh well. 36. I guess that works. Okay, so try this again. So you can, there's this tool that's probably pre-installed called OpenSSL. You can go to OpenL RSA help to see some of the arguments. And so we pass in the public key we got and tell it to give us the key that's in it as text. So here we have the public key and the exponent. So then to get the factors, you trust in Wolfram alpha. Yep. Now to get to get the private key, you have to do some calculations with the private key that I'm not entirely sure how they work, but this is the internet, so someone wrote some stuff to do that, which I just found online.
That's half as many, at least.
Yeah. So I have like P and Q here, and I use this function to calculate a number called D, which is used for decrypting. And then for each of the encoded numbers, I go to Wolfram alpha again, and the way the way RSA works is to encrypt something. You take the message as a number, raise it to the power of the exponent e with modulus n, which is another part of the public key, and to reverse it, you again raise the encoded number now to this d we got with the magic calculation, and again use n as a modulus. So here's the one of the numbers from the encoded file, and then I go and raise that to this number and say modulus n, which we got earlier when using OpenSSL. Here, that's this one. And so you get a number from this, and so I can copy this somewhere into here and get this as a hexadecimal number, and paste that into a hex editor, and there's the first part of the key. And so you repeat that for all of the parts and like stick the key together.
Awesome. Thank you.
Yeah, I got this one where I found out what E was, and then I couldn't figure out how to get E from Z, and I just ran out of time, and at 1 a.m., and I was like, challenge,
I got part of the way there, but that was hard.
The download link and open the slides this week is the link to last week's challenge.
We learned what a Caesar cipher was.
He just pointed me at you.
You're right. 1 second.
All right. I'm showing hard 2 now.
Yeah.
All right. You guys want to see hard 2?
Yes.
Okay, so for hard 2, you guys were given this JPEG hard 2, right? So that makes you guys think of steganography, hopefully, because that was in our slides. So if you tried a lot of the popular steganography tools like StegHide and stuff, those wouldn't work. So, because what Joel and I found was a Python library actually called steganography. Okay, so what you do is you run pip install. I can't type. You run pip install steganography, and that installs the Python library. Then you can run steganography, and then just -d. That's for the D code, and then hard2.jpg, and then let it run. Give it 1 second. Give it a second. Give it a little more second. It works, I promise. You just gotta give it a second. All right, so you get this garbage, right? So the hint was what could possibly be better than I can't copy things. The hint was what could possibly be better than Comic Sans MS, right? So, and then the next hint we released on Thursday was try Word. So you paste this into Word just like that and change your font to Wingdings, and oh, look at that, everything matches. And the best part about this is you cannot type this Wingdings into an online converter. It'll pop up as empty boxes. You have to go through by hand, type out all the alphabet, and you get this. What does that look like to you guys? Base 64. Okay, so you take that, go to the best website ever. Whenever you convert it, you get this Spanish phrase, SOCKS. Okay? Anybody have any idea what that is?
Translate.google.com.
Okay, yeah, if you translate that, you're going to get something like that's what it is, or that's it, or something like that. But sound it out. What does this spell? SOCKS. What does that spell?
Socks.
Socks. So, if you got that far, all you had to do was go to the website, wrap it in RC3 brackets, all caps socks, and that was the flag. I know Ryan got all the way to the SOCKS part, but he didn't try. He didn't try wrapping it. Got it. Hey Ryan, since you got so close, you want to show Easy 3?
No.
So I could not get Easy 3 to work for some reason because I'm dumb and don't really know XOR all that well. But basically, you can run hex dump on the easy3.enc, and then you get all this hex, and then everybody knows how the flags look. It's RC3 curly brace, right? So I can't remember exactly how you do it, but you take these hex bytes and you XOR them with the known thing, because capital R would be the first byte, right? And so you XOR them and it does the bitwise comparison. And then it'll kick back a key, the XOR key, which is 5b in hex, 5 lowercase b. And then you use that to undo the encryption and you get the flag. Any questions?
I have no idea.
Everybody good? Any others? All right, cool.
So we just transitioned to this new thing that Google touted as being super cool and helpful called Team Drive, and turns out we can't just randomly share stuff from the Team Drive with you guys, so we're moving it back to the old drive. It'll be up, the challenge will be up in like a minute.
Yeah, Team Drive is really buggy.
Rip Google, yeah.
We adopted it on day 1 because we're cutting edge and agile.
Early adopters.
Bleeding it. Yeah, we all run Gen 2.
You also call your own.
Yes.
You can't move folders in Team Drive.
So Brad, having not watched the
Write your own kernel. You should just stop using it.
yeah, you're right.